Hello, welcome back to the channel. Last time, we introduced the Unsloth $500,000 per year LLM Engineer Job Interview Challenges series. Today, we're diving deep into the first challenge, converting a model's weights from NF4 to FP16 or BF16 within a single Triton kernel. This might sound a little technical, but it's super interesting, and I'll break it down step by step. The first task requires us to take model parameters, initially in the NF4 format, and convert them to a more standard 16-bit floating point representation, either FP16 or BF16, all within a single, efficient Triton kernel. Before we jump into the Triton specifics, let's understand what NF4 is and why it's such a big deal in the world of large language models. Why would we even need to convert something to or from NF4? The whole concept of NF4 comes from a groundbreaking research paper called Q-Lora, Efficient Fine-Tuning of Quantized LLMs. Q-Lora is all about making it possible to fine-tune these massive language models without needing a gigantic, expensive cluster of GPUs. The key innovation is NF4, which stands for 4-bit NormalFloat. The core idea is incredibly clever. Represent the weights, the parameters, in your neural network using only 4 bits of information. That's incredibly small compared to the usual 32-bit, FP32, or even 16-bit floating point numbers we often use. This drastically reduces memory usage. Okay, so how do we actually take a regular floating point number and squeeze it down to just 4 bits? It's a multi-step process, building on the concepts we briefly touched on in the previous video. I used Claude to create this interactive web app. Let's walk through it. 1. Flattening. Think of your model's weights as a large matrix, or, more accurately, a collection of matrices. The first step is to flatten that matrix into a single, long vector, a one-dimensional array. This makes it easier to process in blocks. 2. Blockwise quantization. We then divide this long vector into smaller, equal-sized blocks. A common block size might be 64, but the specific size can be adjusted. The key is that we're processing the weights in these manageable chunks. 3. Scaling, finding the maximum. Within each block, we calculate a scaling factor. This is done by finding the maximum absolute value of all the weights within that block. This maximum value will be crucial for normalization. 4. Normalization. We normalize each block by dividing each weight in the block by its corresponding scaling factor, the maximum absolute value we just found. This brings all the values within the block into a range between -1 and 1. 5. Quantization. This is where the 4-bit part comes in. We have a predefined set of 16 discrete levels, which can be represented by a 4-bit binary number. Each normalized value from the previous step is then mapped to the closest quantized level. We're essentially rounding the normalized value to one of these 16 predefined options. Now, you might be wondering, where do these 16 specific quantization levels come from? The Q-Lora paper states that these levels are chosen to approximate a normal distribution, also known as a Gaussian distribution. That's why you'll see that the levels are much closer together near 0. This is because, empirically, the weights of a trained neural network tend to cluster around 0, with fewer values further away. By having finer granularity near 0, we minimize the quantization error for the most common weight values. So we've squashed our floating point numbers down to 4-bit representations. How do we get back to a usable floating point number, like FP16 for actual computation? This process is called dequantization. It's relatively straightforward. We multiply the quantized 4-bit value, which represents an index, into our table of 16 levels, by the scaling factor we calculated earlier for that block. This brings the value back into the original approximate range of the weights. Of course, there's a trade-off. This quantization process introduces precision loss. We're approximating the original floating point values, so there's inevitably some error. The clever design of NF4, with its normally distributed levels, minimizes this error for typical neural network weights, but it's still there. The benefit, however, is a massive reduction in memory footprint, which is crucial for working with large models. And that's a high-level overview of NF4 quantization. I know it might seem a bit complex at first, but hopefully, this breakdown makes the core concepts clearer. Later in the series, we'll dive into the actual Triton code implementation, and now you'll have a solid understanding of the underlying logic. We'll see how to efficiently perform this conversion in a single kernel. Don't hesitate to leave any questions you have in the comments below. Thanks for watching, and I'll see you in the next video.